Let's wait a few seconds and it will start. Yes. Muito bem. Boa tarde a todos. A palestrante acaba de chegar. Nós vamos começar, então, a palestra da tarde do colóquio. So it's my pleasure to introduce Professor Maria-Luisa. Professor Maria-Luisa, she did her... Oops, sorry. I have a second speaker working here. So Professor Maria-Luisa, she did her bachelor and master at the University of Zaragoza in Spain, and her PhD as well. And after that, she went to a postdoc in Germany, and she worked at the University of Göttingen with a colleague of mine that was here in Florianopolis and talked at this very same colloquium years ago, Professor Hohage. That's the time point when she started working with inverse problems. And before getting her current position, she had previously positions at the University of Zaragoza and Navarra and at the UCM, the Complutense University of Madrid. And so next week, the speaker is also had his formation at the Complutense, so, but he's from dynamical systems. Anyway, so currently, Professor Maria-Luisa, she has a professor position at the School of Aerospace Engineering at the University Politécnica de Madrid, and she started 2010. Her expertise areas are boundary element methods for simulation of scattering and thermal waves. She was awarded a few prizes in her scientific career. In 2008, the Eurasian Association of Inverse Problems Young Science Award, and 2010 Young Science Award for the Spanish Society of Applied Math. So it's my pleasure to introduce Professor Maria-Luisa. I cannot see your slides, so I don't remember the title of your talk.
Okay, I'm going to show now. Okay, can you see it now?
Yes, let me see. Okay. Today she's going to talk about topological derivative-based methods for inverse multiple scattering problems. Thank you, Maria-Luisa, for accepting the invitation, and the floor is yours.
Okay, thank you very much. No, I need to thank you because of your very kind invitation to participate here. I wish to be in Florianopolis, but I'm at home, but I hope to visit you when everything goes better. So by the moment, I'm going to talk about this topological derivative applied for inverse scattering problem, which indeed you already had a talk in this colloquium given by Professor Novotny. So I'm happy that he introduced you in the subject. But my application is going to be different. It's going to be for obstacle recovery. So let me introduce first the problems we are going to deal with. So the idea is that in general, we will have a medium that I will call R with some obstacle inside. And the objective is to determine how many objects we have, how big, where are they located, that is to get as much information as possible. And as you can imagine, the range of application is huge. So you can think in medicine, where the objective is to find some tumors in the body, or in geophysics to look for oil or gas, or in general in materials, which is more the application in my aeronautical school, where we try to find inclusions, corrosion, and so on inside the materials. So the general idea for these scattering problems is that we will produce some kind of incident wave. So we control the experiment, we excite our sample where we don't know if we have some object or not. And the idea is to look how this wave interacts with the medium, to look at this wave and to check if there is some transmission, some attenuation, or what is going on. And we will take some measurements at some detectors. So I will call inverse direct problem, sorry. So the well-posed problem, let's say, when you know the shape of the object, the size, the location, so you know all the physical properties of the objects, you know the geometry, and you want to compute the response of the system at the receptor. So when you want to simulate what you are going to recover. This is a well-posed problem in the sense that it has a unique solution that depends continually on the data. This means that if you change slightly the conditions, for instance, if your object is slightly different, or if the material is slightly different but very close, then what you are going to detect is going to be almost the same. However, we are interested in the inverse problems. So the idea now is that we have some measurements at some receptors, and what we want to find, we want to identify the regions for which this forward problem agrees with the measured data at the observation points. So now our domain is an unknown, and this becomes the problem much more challenging. So now this is what is called usually an ill-posed problem. That means that it may not have a solution. So maybe if I have my measurements, we call that our machine, the machines that you use to recover in practice data, but have some, they are not perfect, they also have some noise. So maybe there is not a solution for these measurements. And also maybe there are different configurations that can get the same kind of information. So the problem is much more complicated, and one cannot in general assure that there is going to be only one solution, or that it depends continuously on the data. So depending on the perturbation you add, maybe the solution is going to be completely different. So the idea is that we have to deal with something more complicated than when solving direct problems. Okay, and the idea to distinguish between our obstacles and our medium is that, of course, they have different physical properties. So depending on what we are thinking, for instance, in acoustic scattering, the difference comes in the elastic constants, or in electromagnetic scattering, we have different electric conductivity or permittivity, or in thermal scattering, the parameters corresponding with the thermal situation. And depending on the application, depending on the situation we can apply different, kind of incident waves. So we can think in acoustic excitation, in electromagnetics, by heating the objects, and so on. But in this talk, I'm going just to talk about two model problems. One, the most standard one, is dealing with time harmonic acoustic waves, but I also want to show you some experiments for the electromagnetic case. And all the details are basically in these three papers, which are with my collaborator Ana Carpio. This first is devoted to the acoustic case, and these two ones with Frédéric Leloir from the University of Compiègne are for the electromagnetic case. Then I'm not going to show you any proofs, so I just want you to give an idea about the method, an idea of what we can obtain, but I don't want to show you the details because are too complicated just for a short seminar. So let me fix these two model problems. So the first one, the simplest one, let's say, is the time harmonic acoustic wave case. And this means that we will generate acoustic waves, that is solutions to the well-known wave equations, which is written here, but most of you know it. This is the wave speed. And the idea of this time harmonic is that we will look for solutions of these equations that are given by this form. So we have a time dependence given by this frequency omega, and the space only appears in this function un. So this is the complex amplitude of this incident wave. So in time, we are not going to solve anything in time because we know how is the dependence. It's something time harmonic. And this will be the important part that we will use. And we further assume that our excitation is given in one direction, and this is a planar incident wave. Then after some time, if we excite the medium by this kind of wave, then the behavior of the total wave is also time harmonic. So it can be expressed as the real part of this exponential function depending on time. And here is the dependence on space. So if we substitute this expression here into the acoustic equation, then we get this other well-known equation, which is the Helmholtz equation. Here is the Laplacian. And this number k is the so-called wave number. So this is the equation that will model our first problem. It's just the Helmholtz equation. And the idea is, for instance, to look at what happens when I have some obstacle in the medium is like this. So this is how an incident wave looks for a wave number 4. This is a planar wave in this direction. I'm showing here the real part of this wave. And here is what happens depending on which kind of object I have. So in these 3 cases, I have exactly the same shape for the object, but the nature of the object is different. So the first one is described by a homogeneous Neumann condition, which means that it's a sound hard object. This is a sound soft one for the Dirichlet problem, and this is when we have some transmission condition. In the end, what I want to emphasize here is that my incident wave was propagating, and you can see that it's the same behavior everywhere, but when my material properties change, for instance here, what happens is that we find some perturbation and then we observe a different behavior. But of course, when you have some detectors, you don't have detectors everywhere. You only have a few. For instance, imagine that we are on the ground. So this is a section, and you can only reside, we have all the microphones here. So we will observe, here is the incident wave. This is what we will obtain when we recover the transmitted wave here. This is the total wave here. And from this information that I see that is different from this other one, I want to determine that I have one object, that the object is located here, and also that the shape is the one that we can see now, because we know the object in this case. Okay, and the same happens for other conditions and for other kind of objects. So we just see that there is a perturbation that we can compare with the incident wave. For instance, here we see that the perturbation is very low in comparison with this case. But anyway, this is from this information, we want to recover the number of objects, the size, and so on. Okay, so given more details, the direct problem, so the one where you know everything, where you know the kind of incident wave we are generating, in this case, a planar incident acoustic wave is given by this expression. So here is the wave number, kappa, and D is the direction of the incident wave. And if we know the object and want to reproduce what we are going to measure at the receptors, then we have this model problem. So here we have the Helmholtz condition, the Helmholtz equation that we have seen before, and I will have to fix the ideas. I'm going to impose here the Neumann boundary condition. Okay, this is just to select one problem. It's the same if we could select any other one. So, but for the moment, we will consider that we have Neumann condition, that we have sound hard objects. And this condition looks strange if you are not in the field of the scattering, but is the normal, the habitual condition, and it simply says that my waves are decaying at infinity. So it's the so-called radiation Sommerfeld condition at infinity, and it's just a standard condition to say that my waves are decaying. Okay, so the direct problem is just to solve this problem when you know the object. The inverse problem, the one we want to solve, is is given as before. So the idea is that we will get some measurements at some receptor xj, and we want to find the object such that the solution U to this problem agrees with our data at our receptors. So we have here n receptors equations that we want to be satisfied, and values that we want to fix. Okay. For the electromagnetic case, we have a similar problem, but this is much more complicated because now for the mathematical model of the propagation of electromagnetic waves, we have to deal not with this kind of scalar function. Now we have these vector fields, the electric field and the magnetic field H, that are related by the Maxwell equation. This is a system of equations. So now we have 6 different equations that are coupled to each other because each of them has 3 components. And from this system, we have some parameters here that are written. It's not very important. It's just to have an idea of what kind of problem we have. And the thing is that, again, we can think in time harmonic excitation. So again, we can think in time harmonic incident waves, and then these vector fields behave as time harmonic as well. So we have the time dependence given by this exponential function, and now this complex amplitude is now a vector, this E and this H. And if we introduce these two functions into the Maxwell equations, then we get this system where we don't have time anymore. And now from here, in this fourth equation, we can write this H, this magnetic field, in terms of the rotational of this function G, and substitute into this equation. Then we get finally this second order equation that resembles the one for the Helmholtz equation, but now we have here this double rotational. And in the end, what we have is a system of three equations that are coupled for the three components of this function G. Okay, so the unknown now will be the complex amplitude for the electric field. And again, we have here a wave number K defined in terms of these parameters. Okay, so here is this will be our model problem. So again, we will have an incident wave, which will be again a planar wave. Now a planar wave is described by this function. So again, we have the direction D, but we also have a polarization vector P that has to be orthogonal to the direction. And the direct problem is as before. So the idea is that we know the object, we know the parameters, so we know the value of this kappa. And to compute the electric field at some observation points, we just need to solve this Maxwell problem where I'm imposing again a Neumann condition to model a cavity inside this domain R3. Okay, and this condition also looks similar to the one for acoustics. Now this is called the Silver-Muller-Radisson condition, and again is a decay condition, which is standard in this kind of problems. Okay, and for the inverse problem now is the same as before. So the idea is that we can measure this electromagnetic field at some points, at some receptors, and we want to find the solution to the direct problem is such that it agrees with our data at the receptors. Okay, so the general setting is exactly the same. The only difference is that the problem is modeled by the equations that appear for electromagnetic cavities or by the equation that appear when dealing with acoustic waves. Okay, so let me show you now how to deal with this kind of problem when using these topological derivatives. So first of all, I need to introduce them. And the idea first is to consider that, again, I wrote here the idea, is that we want to find the objects such that our objective is to find these cavities such that our data agree with the solution to the forward problem at my receptor. So here this V can be the acoustic pressure or can be the electric field for Maxwell. And the idea is, well, this is very restrictive. If I want exactly to have here the equality, maybe I will not have a solution, or maybe it will be very, very strict and I will find a solution that does not fit with the reality. So what one can do is to use a weaker formulation where instead of trying to find here an equality, we just want to try to minimize this functional. So now we are looking at the least square cost functional. So here have the differences squared. And the idea is to find some minimum of this function. So this V is the solution of the Helmholtz or the Maxwell system. And now the domain omega, my objects, appear here due to this function V, and the Helmholtz or the Maxwell system are related and appear as a constraint. So now the idea is to try to minimize this functional, and as you can imagine, there are lots of different possibilities to try to minimize this kind of least square functional. So most of them can be interpreted as gradient descent techniques or related to, and they basically differ on how we start with an initial guess and then we are changing it from one iteration to the other to try to get a decreasing sequence. So the first attempts which I'm calling here classical deformations, are the idea is that we start with some initial guess, with some object that we think that we can have, and then we start to change it in a smooth way. So the idea then is that you need to know how many objects you have, because you are going to change them in a smooth way. So you cannot split them into two different parts, because that is not a continuous transformation. And this is a problem because in practice, you don't know how many objects you are going to find. So to solve this problem, Santosa proposed a new strategy, which is called the level set technique, in which one has his initial guess, but now you can start to deform and you can obtain changes in the topology. So now the problem of knowing the number of components is not important anymore. But what is true is that you need an initial guess to start the algorithm. And if this initial guess is not somehow close to the reality, then the evolution is slow. So usually you need a lot of iterations. Let's say a lot could be hundreds or maybe 1,000. So it's costly in general if you don't have a very good initial guess. So to overcome all these problems, I'm going to explain you these topological derivative methods, which have two main advantages. First of all, they provide good initial guesses, so you don't need to have any a priori information. You don't need to know how many objects you have. You don't need to know where are they going to be located. And also these initial guesses can be iteratively improved in a very few iterations, as I will show you in the examples. Okay, so let me start with this definition. So the definition of the topological derivative is here, is somehow strange, but you have already seen it from Novotny's talk. And what you can see is the idea that we have some region where we want to look for my defects. And the idea is to make in this region a small perturbation, which is a ball of radius epsilon located at each point. Then at each point, I want to look at the difference between the value of the functional when I have this small perturbation and the value of the functional without this perturbation. Then I compare these two quantities, which of course depends on epsilon, and it's small because this ball is small. And I want to know the size of this. So this topological derivative is defined as the limit of this difference divided by this function f here, which is something that you choose in view of this asymptotic expansion. So basically, you choose it to guarantee that this limit exists, is not equal to 0 everywhere, and this function goes to 0. So this looks strange, but in the end, these functions are very simple. For instance, in our two model problems for the Neumann problem in acoustics and in electromagnetism, you just need to take the volume of the ball, or the size of the area of the ball in 2D. Okay, so this function is just the area in 2D or the volume in 2D. Okay, so the idea here is again the definition, and the important thing is that for each point x, for each point of the domain, we have some real number. So you have a scalar function of x, and this number measures the sensitivity of the functional to removing balls around x. So the points at which this topological derivative will attain large negative values will be identified as points that belong to my object. Maybe this is not clear from the definition, but look here again. Imagine I can take this limit out, multiply by this f, and then I can write this expansion, which is exactly the same as the definition, but now what I see is something like a Taylor expansion. Sorry. I can see that when I remove the ball, I have the value in the full domain plus this first order term. And here, since this function f is positive, then if this topological derivative is large and negative, then this factor in red is also large and negative. So this is saying that up to the first order, the cost functional is decreasing. Recall that we are looking for a minimizer. So this means that this point is interesting for me. So I'm not going to minimize anything. I'm not going to look at method to find a minimum by an iterative method. I'm just going to evaluate this topological derivative and look at the points at which this functional is decreasing. And then I'm going to consider as an approximation of my domain the set of all the points for which this topological derivative is large and negative. And large and negative will be defined by this condition here. So I will look at the largest negative value, and this is just a percentage of it. Okay, so let me show how does this look. So I'm going to show you an experiment, which is for the electromagnetic case, for the wave number kappa equals 3. And the idea is that I have these two objects. Recall that this topological derivative gives for each point a value, a real number. So I'm going to plot this, I'm going to consider in this cube a mesh of points, and at all of them, I'm going to evaluate this topological derivative. So I'm going to show you the values of the topological derivative at points that first belong to planes of the form x equal a constant, then y equal a constant, and then z equal a constant. And I'm going to show you then some color maps, and the largest negative values correspond to the largest negative, with the blue colors are the largest negative values. So this is a movie where we can see here now x is constant, and we see that when we don't cross the objects, the value is red, so it's not large and negative. But once, look here, now we get these large negative values, these blue colors that are indicating that my object should be located in this region. So you can see that this indicative function is locating perfectly where are these two objects. Indeed, it seems that we already can somehow see the shape of this object. Okay, so let me show you, this is the same experiment, but now just some photographs of the movie. And so here you can see that indeed we have seen in the movie that the largest negative values were indeed inside this object. Here are the two objects, this one that looks like a bin, and this, because this is bigger in size. So here maybe you can see better that the largest negative values, the blue colors, are inside this bin. And the idea for the approximation is that we will keep these largest negative values. And what does this mean? That I'm considering here the largest one. So here, maybe this here, this value here, and this is a percentage. So for one of them here, when C0 is equal to 0.3, I'm maybe cutting somewhere here. So all the dark blue color are identifying only this small region, which corresponds to the interior of this domain. If I increase this constant, then I will keep more points, because now this percentage is bigger. So now this is increasing. And finally, for a large negative, for a large constant, then my reconstruction has the correct number of objects, and somehow not the shape, but the location is very good. So we will have to calibrate somehow this constant, but just to give an idea on how this works, I will just evaluate this topological derivative at some region. So here this aeroesp is the cube where I show here, so the cube for my movie. And for all these points in the cube where I evaluate, I keep the ones for which this derivative is large and negative, okay? Okay, so let's go back. Here is my definition. This is what, but from this definition, I show you this beautiful movie, but there is something between. You don't know how I compute this in practice, because I just show you this definition, which, as you can see, is very, it's not practical from the computational point of view. I cannot, for each point x, try to compute this limit for a given sequence of volts. This is just a definition, a theoretical one. In practice, what you should do is to try to find an expression, a closed form expression that you can implement numerically. So in this case, the idea is to try to find it. And what we did in the paper I mentioned before is to find these closed form expressions by using an equivalent definition of the topological derivative in terms of shape derivative. So it can be seen that this topological derivative is a limit of shape derivatives, and after that compute using some asymptotic expansions. this is long. It takes some pages to get all the proofs, all the details. So I'm not going to show you. You just, if you're interested, please go to the papers and take a look. And you can, of course, ask me later by mail or whatever. And what is important for me is just to show you how it looks, how difficult or how easy is to implement then from the practical point of view. Okay, and what we are going to see is that in the end, we obtain very simple formulas, very easy to implement, that only involve the solution to a direct problem and to an adjoint problem. Okay, so let me show you now how this derivative looks for the acoustic case. Okay, so here, what we prove in this paper, in the first one in the list, is that to compute the topological derivative at any point of the plane or space, depending if n is equal to 2 or 3, is that you just need to evaluate this very simple expression. Here, we have only two functions, this uinf and this w. And this function uinf indeed is just the incident wave. The wave that we are generating is the planar wave. So it's just this expression that I know perfectly. So for each point x, I just need to evaluate this function that I know. And this other function, this is the solution to a related adjoint problem. And it's also known in closed form. The solution of this adjoint problem is given by this expression here that, as you can see, it involves the difference between our measured data and the values of the incident wave at the observation points, at the receptors. So to implement this, to evaluate this part here for each point x, this is also very, very simple. I just need to evaluate the incident wave, so this expression at the receptors, and I need to evaluate the Green's function for the Helmholtz equation at this difference between the position of the point and the receptor. And this function g is known. So it's given by the Hankel function of the first kind and order 0 in the two-dimensional case, and is given by this function here for the three-dimensional one. So again, to implement this is really, really easy. In MATLAB, it's just a few lines because all these functions, the Hankel functions, are also implemented. And for this other term, we only need to compute the gradient of this function, so the gradient of this exponential. This is also very simple, and the gradient of this function uinf, which is just the gradient of this one, so the gradient of this function here that again is known. So what I want to emphasize is that we don't need to solve any problem. We know these functions analytically. We know which functions I need to evaluate. So to compute, to generate my movie, I just took a grid of points. I just evaluate these two functions and multiply them, and the gradient of these two functions and multiply them, compute the inner product. And for each point, I get one real number, and this is what I'm plotting. So from the implementation is really, really simple. It's almost for free, which means that I don't need to solve anything because I know these two functions. And also to emphasize that our data are included in this topological derivative via this adjoint problem here. Okay. So let me show you some other reconstructions. So the first, here in the first one, we see what happens when I'm considering only a few receptors. So here I think that there were 15 receptors and only 12 in different directions. And we get these large negative values, which are inside this region. So we get somehow a good idea about what's going on. We can observe that we only have one object, and somehow, depending on the level we choose here, we can recover even the shape. In case of having more than one object, then the problem becomes more complicated, especially when you have objects of different size. For instance, here, we can observe that the largest negative values, the blue colors, are concentrated inside these two regions, which corresponds to the regions of the bigger objects that are also close to my receptors. Okay, and this object is not seen by my derivative. And we observe in this third example that when we have some limitations, for instance, if we can only locate our receptors here in this part, then what happens is that as one can expect, is that we get more information about the objects that are closer to the receptors. So now this object that is farther from the observation points and also in the shadow of this object is not seen. Okay, and in this case, the level of noise was at 1%. So we observed that we can get similar results when we locate the receptors farther, if we include more receptors or more incident direction. And which is very interesting is that we can also add a high quantity of noise, and the method is very robust. So these reconstructions are not very dependent on the level of noise. We can have very noisy data and get similar reconstructions. In 3D, in acoustics, we get similar reconstructions. In this case, for very simple shapes like a sphere, like here, we observe that we are perfectly recovering the size, the shape, and everything, and the location. For the electromagnetic waves, we have a very similar explosion here that involves the inner product of the solution of the problem without any object. So this is the incident wave, is our planar wave, and we have here the counterpart of the acoustic case, but here for electromagnetic waves. So again, we have a solution in terms of the green function that we can also implement very easily. These are some reconstructions where I want to emphasize that depending on the size of the object or the shape, maybe the reconstructions are nice, like here. In any case, here is for the wave number equal to 3, here the wave number is 5. What I want to show is that when shapes are very close to each other, they are different. You can see that here the section is a rectangle and here is an ellipsoid, but it seems that I have two ellipsoids here and also in this part. So maybe for shape, this is not a very it's not very sharp, but I'm just only evaluating these two functions. Okay, and here, which is also interesting, is to look what happens when I reduce the number of waves or when I reduce the number of incident directions. Then what we can see is that, for instance, here is very clear that in the second row, when only I'm considering receptors with y greater or equal 0, so I'm only in a part of the sphere, then what happens is that I can only see the part of the objects that are close to my receptors. So the reconstructions seems to be very small, even when increasing the constant. So the problem is not the constant. The problem is that I cannot see this part of the object, which is not in the part that is illuminated or in the part that is close to the observation point. So let me show you now how I can improve my reconstruction by iterating this procedure. So the idea now is to try to improve that. So at the beginning, I compute the largest negative values and keep them. The idea now is, once that I get this initial guess, now that I have some kind of initial guess, I want to include them in the model and try to improve my reconstruction. And what we prove is that if I introduce them in the model, then I can compute a new topological derivative with my approximate domain and try to include some new points. And what we found is that we get exactly the same expression as before, but now these functions U and W are solutions to a direct and to an adjoint problem, which look as the original ones, but now they take place in the approximate domain. So now to implement this topological derivative, now is not for free. Now I need to solve two problems. I need to solve the direct problem and the adjoint problem when my object is this first approximation that I have just computed. Okay, so this is cheap. I have the same functions for all the points, but I need to solve two problems, one direct and one adjoint one. And for the Maxwell system, we again get a formula that looks exactly as in the case where we don't have an approximate domain, but now again we need to solve the direct and the adjoint problem, but taking place in the approximate domain. Okay, so the reconstruction strategy in the end is then to initialize as before. So we compute the topological derivative with no objects. So we evaluate these incident waves and keep the largest negative values. And now what we do is to compute the new topological derivative for the current approximation. And then we define the new objects as the union of the current one and all the points for which now the new topological derivative is taking large negative values. So the idea is that I'm going to increase to add the points that could be missed from one iteration from the other. Okay, and of course we need to check that my functional is decreasing. We call that in the end I'm trying to find a minimizer. So if I'm taking too many points, if my approximation is too big, this functional is not going to decrease and I'm not going to accept this object. So I will reduce and only include a few points. Okay, and this algorithm will stop either if I have more iteration than I want, and also by the discrepancy principle, which basically says that I need to stop once I get an approximation that satisfies my proximity with an error comparable to the error that my data has. Okay, and now at each step, I need to solve a direct and an adjoint problem. Okay, so let me show you how this iterative method works. So I'm again in the acoustic case with these observation points, and where my first computation show me that I have here some kind of object. Okay, so this is without the crosses, but it's the same plot. So now in view of this approximation, if I keep the largest negative value, something like all the values below in dark blue, then for instance, my first approximation is given by this gray ball. Now, what is interesting is that a new set of points are appearing here with large negative values, which means that now my object is bigger. So now in the next step, my object is going to go in this direction. Now in the next one, I see that this is getting bigger, bigger, bigger. So this is the 5, 6, 7, 8, 9. At the end, at the 11th iteration, what I see is that my object is very close to the real one, and the shape and the size is also very satisfactorily recovered, and only, which is important, in 11 iterations. So in the end, I only need to solve for each incident wave, they were 12, I need to solve a direct and an adjoint problem. Okay, for the Maxwell system, we have also very nice reconstruction. So I'm going to show you what happens in this case. So as you remember, this is the movie before where we observed that all the largest negative values were concentrated inside this object here. So my initial guess, depending on the constant, only has one object here. Okay, this is the movie, so I'm going to stop it. Okay, so the first iteration only has one object, so we don't need to start the algorithm with the true number of objects. And what we observe now, if we introduce this object and compute the new topological derivative, then we observe that now we start to observe clearly that we have another object here. So in the next iteration, I have the correct number of objects and they start to look to the true configuration. This is my approximation after 2 iterations, 3, 4, 8, 13. Okay, so we observe that we are getting some blue regions from one iteration to another, pointing to the points that I need to include. So here is a summary. So this was my true configuration. This was my initial guess, and this is what I obtained after 16 iterations. So you can see that the reconstruction are really, really similar to the true one, and only we use 16 iterations. And here we can see how this caused functional decrease and the algorithm stopped because of the discrepancy principle. Here is how the iteration looks for this more complicated case where I have only observation points in one region. So at the beginning, I could only see the part close to them. But after the next iteration, I start to see first the second object that was not seen. So in the first iteration, I have 2 small objects. And what is interesting is that in the next iteration, I start also to see this part that is not directly illuminated. So now in this intermediate step, I have indeed 3 different objects. So at the beginning I had 1, then I had 3. In the end, I will have only 2. And this is how it looks, the iterative procedure. So here is when the algorithm stops. Here is my approximation after 17 iterations. And we can see that the reconstruction is not completely smooth, but it's nice taking into account that I only have a very few information only on a part of the sphere. And this is my final example where I want to show you how the method works in very complicated situations where I have more than one object. Indeed, here I have 8 different objects that are very close to each other, and also they have different sizes. So here it's very complicated, especially to obtain these small spheres that are in the middle of everything, and also they are very small in comparison to some other objects. So here is the movie to see what happens. By computing the first topological derivative, we can see that in the large objects, we get large negative values, we get a lot of blue colors regions. But if we look now at the spheres, look here, we don't get any dark blue color. We cannot see this sphere. These colors are green, and they look as green as some spurious things here. So what is going to happen is that our first iteration is only to have a few of these objects. So this is what happened during the iterations. So my initial guess had only these 4 objects. So it seems that the 2 peanuts, these 2 objects, and these 2 spheres were more complicated to identify. And we observed that during the next iterations, at the 3rd iteration, we still only have 4 objects that are found. However, in the 4th iteration, we get the correct number of objects. We have here 8, but we observe that these 4 small ones look like a sphere. This here and here, we get these peanuts, which are indeed big in comparison with the sphere, but at this iteration, they look the same size. But we observe that after a few iterations, at iteration number 9, we start to devise the geometry, and after a few iterations more, at iteration 19, this is my reconstruction, and after 28, this is what I get. So we can observe that even in this very demanding situation, I get a good reconstruction of all my 8 objects. And here is how was the decreasement of the cost functional during the iteration. It is also interesting to look at the noise level. So here it was a 1%, which is reasonable. It's also interesting to see that when I increase my noise level to a 10%, then we are able still to find a good approximation of all the configurations. So now the reconstruction is not as sharp, but it's very nice. We get somehow the shapes, they are all perfectly located, and only the shape is not perfect. We also observe that the iteration stopped early due to the discrepancy principle, and also since my level of noise was higher, then the iteration stopped also earlier than in this case. So just let me conclude, it's a little bit late. So yes, I hope you get the idea that this topological derivatives is a very powerful tool to solve inverse problems when you want to find some objects in different areas. So today I was talking about electromagnetism and acoustic, but you can apply to any kind of excitations. You can use it for photothermal excitements, in elasticity, in tomography, and in many, many applications. We have seen that this topological derivative, this one-step method, gives a good approximation without any a priori information. So I don't need to know how many objects, where are they located, and so on. And we have also observed that by iterating this method, we can improve highly the reconstructions, where maybe small objects or maybe complicated parts of the objects were not seen in the first trial. I didn't talk about this today, but you can also combine multi-frequency results. So you can combine results corresponding to different excitations, to different wave numbers, and this promotes very good reconstruction, especially when you only have a very few observation points and a very few incident directions. And finally, I also want to emphasize that I choose these Neumann boundary conditions, but indeed, you can use any boundary conditions. In the papers, we use some other different conditions, direct light transmission, impedance, so that is not important. Important is just the technique. And well, this is more or less what I wanted to talk to you today. So thank you very much for your attention. And if you have any question.
Hi, Maria-Luisa, thank you very much. Yes, actually, one question arrived during the talk. Now, I asked the audience to send questions at the end of the talk, at least that the questions would be answered at the end of the talk. So the first question arrived in the beginning of your talk is from a colleague from our department, Professor Celso. It's on the screen. Can you read it?
Yes. Yes, you are assuming that omega can have several components, so it's not assumed to be connected as you have seen. But yes, I assume that it is closed.
Okay, thank you. Well, while we wait for other contributions from the audience, I have a question myself. So you mentioned several applications and several different mathematical models where you can apply this reconstruction method. So what are the methods in which this method, what are the problems in which this method is most used or produce better results?
I think in the ones I show you. So in acoustics and electromagnetism. Okay, for instance, we have used it in photothermal problems. So when you look with a thermal camera, you can take a picture, you get a thermography. And if you try to process these thermographies, then what happens is due to the diffusivity of the heat equation, then it is much more complicated to get the position of the objects. So it somehow show you that there is some damage. It somehow localized the places where you have, but you cannot get such reconstructions as the one as I showed you before.
I see, I see. Yes, and what about inverse scattering? We had a talk a few months ago from Andre, and he was talking about shape derivatives and applications also to inverse scattering.
Okay, this was inverse scattering.
No, this isn't. But what about the application? Does it also produce good results?
Yes, this what I was this scattering problem is just what is called when you produce. So the scattering is just you generate an incident wave. This wave
Yep.
interacts with the medium, and then it produces, let's say, two different waves. There is the transmitted wave and the scattered wave. This case called transmitted, but in the end is the same. So the total wave is the sum of the incident and the scattered wave.
Yes.
Okay? So what is called this inverse scattering is to look at this scattering wave. Is this total wave? Okay.
I see. I see. You mentioned also a reconstruction of several. I see Andre is here in the audience. I remember you just mentioned in your results that you are able to identify several different inclusions in the domain using the method. So, and my question is there a maximum number of inclusions where the method stop working, or can you try for arbitrary number of inclusions?
I can try. I don't need the number in my method. I don't use it. So the method uses it. So it recognizes some regions, and then if they are separated, then there are two different objects. If I have two regions very close, then they are merged. But I don't see it in my method. So I
I
don't
see.
need to impose it. The problem is that if you have a lot of different objects, there is also a lot of interaction between them, and
Yes.
then it becomes much more complicated to find them. So it's not only the number. The number, I think, is not a problem. The problem is how close are one to each other. So if they are very close, maybe they can be identified as just one object, or the other
I
way
see.
around. So maybe here in this simulation at the end, this kind of peanut here, maybe this could be identified as two different kind of balls or ellipsoids. So depending on the quality of the data and depending on the noise level, maybe you just obtain something that looks similar, but maybe has not the correct number of components.
Yeah, in electrical tomography, you have also problems. You do the Dirichlet-Neumann measurements, and you have problems if you have one obstacle that is surrounded by other obstacles. Then you cannot get information from the obstacle that is in between the others, surrounded by others.
Yeah.
This probably is going to be a problem here as well.
So it's simpler to identify the ones that are close to the observation points.
Yes, that makes sense. So Andrea just sent some remarks here, and also a question. about time harmonic equations. Can you read it?
Yes, I can read. Yes. Well, I don't know. I don't know. Well, depending on the wave number you choose, so depending on the frequency you choose for the time harmonic excitation, maybe you cannot see properly the object. So there is a relation between the wave number and the size of the object. So for these reconstructions, I somehow choose wave numbers that were suitable for the size, but it's something that you can calibrate. So it's something that is well known, that there is a relation and how is the expected wave number you need to use for the size. But yes, it works very nicely.
As a matter of fact, there is a follow-up to his question, where he mentions the AIT problem I was just mentioning.
Okay. No, I think that electrical impedance tomography is, let's say, much more complicated problem than the acoustic scaffolding. So I think that any method in general has more problems than in case of be applied for acoustic waves. So I don't know, indeed, we use these topological derivatives in this electrical impedance, and we get a lot of problems. So in some situations, we get good approximations, but the object should be close to the observation points, even if you only have one, and even if it's big, not always you can identify it as clearly as in these other cases. But I don't know, and I also saw that using this second order, the method works much better.
Okay, indeed. Depending on the mathematical problem, you may have different challenges in order to identify problems with piecewise constant solutions. No?
Yeah.
So yes, I remember implementing level set type methods for inverse problems, and depending on the inverse problems, the challenge was always different. Yeah. You use the same approach, but the difficulties are inherent to the problem, not to the approach itself.
Yeah, that's it.
Okay, so I see there are no further questions here from the audience. Would you like to do some concluding remarks?
No, I just want to thank you, and I hope it was great for me. It's the first time that I give a talk, just talking with myself here without seeing any face. So I hope I did not it very badly, and otherwise I'm sorry.
No, this is quite fine. Thank you very much. So let me say farewell to the audience, and please don't go away. I'd like to talk to you afterwards. And let me say it in Portuguese. Obrigado a todos pela participação no colóquio de hoje. Então a palestra está encerrada e nos vemos na próxima semana. Na próxima semana o palestrante é o professor Lourenço, da PUC do Rio de Janeiro, especialista em sistemas dinâmicos, que teve a formação dele na mesma universidade que a professora Maria-Luisa, em Madrid, né? Na Complutense. Ele é membro da Academia Brasileira de Ciências, enfim, eu acredito, e bastante experiente, acredito que ele vai apresentar uma boa palestra na próxima semana. Estão todos convidados. Então é isso, agradeço a todos pela atenção, e assim a gente termina a sessão